12,000 years ago, at the end of the last ice age, modern peatlands began to form all over northern Europe and North America. In natural peatlands, decomposition processes are slower than the annual inputs of new plant material to the soil, leading to net accumulation of peat. Scottish peatlands hold more than 1.6 gigatons of carbon, which would otherwise have been lost to the atmosphere. However, the importance of peatlands as greenhouse gas storage areas was not generally recognised until the late 1980s, by which time substantial damage had been done to our peatlands. Take a look at the map of Scotland in front of you. All the peat areas are shaded in light brown. 25% of the Scottish landmass is covered in peat soil. Unfortunately, more than half of this area has been affected by human activities such as drainage, peat extraction or conversion to other land uses that led to erosion or changes in the vegetation. Since the mid-1990s, there have been concerted efforts to restore peatlands, with over 150 areas undergoing work until the present day. Andrew McBride leads the current Peatland Action Restoration Programme.
One of the things that happens with a raised bog is the peat that forms that raised bog accumulates year on year, very, very slowly, about 1 millimetre every year. So you can imagine where I'm sitting here, this has actually taken thousands of years to actually accumulate. So what is this peat that's forming so slowly? Well, it's actually bits of vegetation that don't fully decompose. Bogs are very acid, and that's enhanced by the very wet conditions that they form in. This peat is actually full of carbon. When peat is dry, about 50% of the weight of that is actually pure carbon. So this is one of the reasons why we have to look after our bogs, to make sure that carbon actually stays here rather than being given off into the atmosphere and further enhancing climate change. The peat in Scotland's bogs holds about 140 years of Scotland PLC carbon emissions. So all the cars and everything that is emitting carbon is held in our bogs, and what we've got to try and do is keep that carbon there, and in the future the beauty of bogs is they can actually start to hold carbon through the vegetation and that accumulation of peat year after year.
If you look behind you over there, you can see what happens when the peat actually starts to dry out. It started to crack, it started to shrink. And that's partly because it's losing water, but also it's losing carbon to the atmosphere. When the rains do finally come, that won't actually swell back out to its original size. It actually doesn't come back to its normal size because you've lost part of the carbon to it. Up here on this side, by contrast, there's no dry peat. That peat is in its original form. It's actually staying put rather than being released into the atmosphere. So on a normal day, we've got water coming over these things here, and you can see from a wildlife point of view, things like this dragonfly that's hawking down here coming towards me. There it is, and coming towards you, having a look at us, seeing what's actually happening. This is where it's actually hunting for other insects. Underneath this, there is actually a dam. Let's see if we can find it. No, wait a minute. Yeah. There's the dam. Right under there. You can just see the wood showing through. But you can see actually how the sphagnum has actually started building up. And this sphagnum is actually holding as much carbon as trees. If you have 25 centimetres of sphagnum growth like this, you've actually got equivalent of what some full-size commercial plantation trees are actually holding in terms of carbon. So there's a massive amount of storage of carbon going on in there.
Around 500,000 hectares of peatlands have been affected by erosion to some degree. These are shown on the map on the roof of the car in red. We are on our way to just one such area, where large-scale restoration and monitoring is ongoing at Balmoral Estate.
One of my research projects is to see if we can integrate data from the eddy covariance flux towers, like this one over here, with data from spatial mapping of peatlands across the whole of Scotland and the United Kingdom. So for example, in this site, one of our challenges is that while we have maps of where peatland erosion has happened, this doesn't generally take into account just how complex this terrain is. So you can see from my height here just how deep the erosion is. Gillian behind you here is mapping out exactly where the gullies are so that we can start to understand how large an area of bare peat there really is. Just as an illustration, peat is about half of it is pure carbon. So you can see here just how much erosion has taken place. You've lost 1.5 meters of peat across an area of about 5 meters by, oh goodness knows, 20 meters at least, just in this one gully. And there are literally hundreds of these around us. Satellite images will possibly give us a flat image, but that doesn't take into account the three-dimensional erosion in these areas.
Vary is going to introduce how we measure greenhouse gas emissions on such eroded areas with a flux tower.
As the air moves across the surface, there's a lot of friction between it and the ground, and it generates all these eddies. So there's lots of the air down here is rolling around quite quickly. So we need to measure the quick changes, rapid changes in concentration and wind that are causing the gases to either get deposited on the surface or released up. So how do we do that? Well, on the tower here, in the middle, right up at the top, we have that instrument with the little sort of black spider legs. That's a sonic anemometer, and that measures the rapid variations in wind speed that you get as these eddies roll around. And then just below that, there's a sort of white cup thing. That's our inlet, and the air is drawn in through that and gets pulled right the way back to that sort of white tubey-shaped thing with a hose coming off it, and that's our sensor head, and that's where we measure the carbon dioxide concentration. And that instrument works really quickly as well. So the two of them are measuring about 20 times per second, so it's quite rapid. And you put that information together, and you can tell how much carbon dioxide is either being released from the peat bog or getting deposited down into the peat and stored as carbon in the peat. So we have all this information and measurements. And all these go back into the box here, and this is where we store all the data. We need to get that data back to the lab. So in here, we have what you call a data logger. So all the signals from the various instruments come in here, all the 20 times per second, and all that's stored in here. And the logger also does some basic processing on it and gives us some average values and things. And we have a connection to a mobile phone network, and every now and again it sends the data back to the lab for us, or we can dial in and just check that everything's working okay. And because we are in a very remote location, we don't have mains power to keep all the instruments going. So over here we have some solar panels and a fuel cell, and the box at the bottom has batteries in it. We will put all of these data together, the data from the eddy covariance flux towers, which tell us the emissions from one particular site, together with the maps that tell us where certain types of degradation have happened, and that will give us a figure for the total emissions of carbon from Scotland's peatlands in their degraded state. And then, of course, the crucial question is how much of a difference does restoration make? So that's why we're doing all of this work. Harry, how big an area do you think you're capturing around some of these towers?
It's probably up to about, well, on a really windy day, you could be going out to about 1 kilometre or so. But most of the time, it's probably about 300 metres or something, 500 metres.
We are fortunate enough to work at the RSPB Forest and Ard Reserve, where peatland restoration has been taking place since the mid-1990s at landscape scale. In this area, large areas of blanket bog were planted with conifers in the late 1970s and 80s. If you have a look on the roof of the car, you can see in green where such forested areas were.
Came up the Strath, got the track round this little hill, and we're now here.
Here.
This is where all the forested stuff has been felled.
So this map's quite old, isn't it? It still shows all the forestry. Yeah. What are you up to do today?
So we'll visit the flux tower. We'll go and download the data and do the maintenance on that. Should be all quite standard. Talk through it, and then head out to Tallahill as well and do the same there, I think.
Okay.
And then tomorrow we can go to Crosslocks and to Dyke.
Okay. And we're off to do two different things. So one is to get vegetation quadrats at 10 by 10 meter scale, so we can correlate them with satellite data. So a satellite would look at this area just like we are just now on this map, and they would just see 10 meter squared tiny little pixels within each of these areas. So it's to get some ground truthing data for that model. And the second job for today is to put in those things for water level loggers and soil moisture loggers. That just slots in, and that number is 10497. Gillian and I are here because we are trying to find out whether peatland restoration works, and what we're trying to do is assess that at 3 different scales. So what Paul behind us is doing is setting up experiments to check how moist the surface is, to see whether restoration recreates a wet surface environment, and we're going to tie that in with data from satellites, isn't it? And that's partly what your interest is, isn't it? To see if we can link the data together.
Yeah, to see whether the satellite data can actually provide in some way a measure of what we're observing on the ground, but in a much quicker, larger kind of format.
Yeah, so what sort of sizes are the images that we would be seeing from a satellite here? How big a piece of ground?
Well, the ones I'm working with at the moment are 5.5 kilometres by 5.5, so you're pretty close on 30 square kilometres.
Wow, that's amazing. And each individual pixel, each bit of ground that you see, how?
That varies. Each pixel is about, on the older photographs, about half a metre, but it can go down to a couple of centimetres if we use these unmanned aerial vehicles, or drones as they're called.
Wow, that's amazing. So you would be able to see little patches of sphagnum like this on the
higher detail, definitely.
If you can get all this amazing data from the satellites, that only really tells you a little bit about the colour of the vegetation or what stage of the growth it might be in. How do you link that to greenhouse gas emissions?
Well, you'd have to have some kit on the ground, so to speak, your flux towers, and the measuring instruments on them to actually provide you the additional information, because it's no way, that the satellites we're using could provide you that kind of detail,
not straight away.
Carbon dioxide emissions and so on. So, but by having equipment on the ground that's continuously monitoring and recording that data, we can put the two together and actually look at correlations.
So one of the reasons we have these instruments in locations like this for a long period of time is to understand how resilient restoration practices are in restoring peatland to its maximum functional level. So this year, for example, we've had 2 months of very little rainfall, extremely low rainfall. And as you can see, some of the sphagnum here has dried out. This white sphagnum is photosynthesizing less, so it's taking up a lot less carbon dioxide from the air than this green material would do. So already, if you imagine this over the landscape, if you have a lot of desiccated sphagnum, at this point in time, it's not functioning at its optimal level. So you've seen Vari at the Flux Tower talking about how we measure carbon emissions. Our data to date suggests that the youngest restoration sites are still significant emitters of carbon to the atmosphere. The older the sites get, the less carbon they release, which is a good story. And we know that the natural sites, even over the medium term, every year they take up carbon. So they are essentially carbon scrubbers, which is great in terms of mitigating emissions. The advanced restoration really helps to bring up the water level. Our data suggests that on average the water table is 5 centimetres higher than in the standard sites, and it's only 5 centimetres short of what the natural site should be doing. So clearly much wetter, and you can also see it in the cotton grasses flowering abundantly here.
You can see how the restoration areas start to look more like the target state, as you can see it here, although the typical pattern of bog pools, hummocks and sphagnum lawns has not yet reformed.
Sphagnum is an amazing plant. And one particular feature that's amazing about it is how much water it can hold. You can see the water just dripping out of it there. That will go on and on for ages. The way to get the whole amount of water, as you can see, it's a massive amount of water. It's like a sponge. It holds about 25 times its own dry weight in water. If you compare that with a sponge that you've got in your kitchen, that holds about 7 times its dry weight. The other interesting thing about sphagnum is it actually makes the conditions around it more acidic, which actually favours more sphagnum growth and stops other plants from actually growing. Bog cotton is quite tolerant to that, so sphagnum and bog cotton live quite happily together.
It's sphagnum moss which creates this habitat and maintains it in this state, thus allowing this carbon to remain under the soil instead of being released into the atmosphere as carbon dioxide. And the reason sphagnum is able to do this is because of its unique cellular structure at the microscopic level. So much of the volume of a leaf of sphagnum is comprised of these giant dead empty cells called hylocysts, which are strengthened by ribs called fibrils and have pores that let water into them. And this basically allows these cells allow the sphagnum to act like a giant sponge to keep the surface of the bog permanently moist. But it's not just one species of sphagnum we have in the UK. Sphagnum is a genus with perhaps about 200 or 300 species worldwide, about roughly 35 of which we have in Scotland. And it's important to understand exactly what species we do have, because each individual species has a subtly different ecological niche, different requirements for pH and a different desiccation tolerance. So just last month, for example, it was discovered that this species here, Sphagnum magellanicum, as it was called then, is actually comprised of 3 species, and we're going to have now to get used to calling the one we have in Britain Sphagnum medium instead. And this matters because different species have different requirements in terms of ecology, and it's only by understanding what species we have that we can know what the precise function of any individual plant is in the environment.
We have shown the carbon and biodiversity benefits of restoring peatlands, but what about the wider societal returns? And do people actually care?
As a team of social scientists at Scotland's Royal College, the James Hutton Institute, and the University of Leeds, we've been talking to people in different parts of Scotland about their views on peatlands, such as this one. We found that people's views can be complex and that they are often shaped by how peatlands have been used in the past and by how people are using peatlands today. We also conducted a large survey with 1,800 members of the Scottish public. In this survey, we were particularly interested in how people value peatlands for reducing greenhouse gas emissions, for improving water quality, and for the wildlife that peatlands provide. We found that over 80% of our respondents would prefer further action on restoring peatlands over doing nothing, even if it came at a cost to them. We were able to use the results of this survey to quantify the benefits of peatland restoration in monetary terms, and this analysis shows that the benefits on average outweigh the associated costs. Or in other words, it shows that there's an economic case for restoring peatlands for the benefits that they provide to people in Scotland.
Peatland restoration is costly. On average, a site takes around £800 to restore per hectare. But it is a very effective means of raising the water table and a very effective means of lowering carbon emissions, as we've seen. And Andrew McBride from SNH can tell you more about the associated benefits. So back to Andrew at Blorehorn Moss.
By blocking our ditches, for example, and then filling up with vegetation, rather than the water rushing off and peat being washed off site and off into the burns and into our water supplies, which inevitably Scottish Water will actually have to clean up before it comes out of your tap. We're actually doing the cleaning up here at quite a low cost, and that cost is not necessarily transferred to people who are paying for their water. And also there's an added bonus that we're not having to put so many chemicals into our water to actually clean it up. So there's lots of benefits from doing peatland restoration, not only just wildlife, not just carbon, but also we're getting the benefit from the people who are doing restoration for us are actually seeing the benefit, like farmers from the point of view of stock, which are grazed on here. They don't lose so many lambs in the ditches, because basically when the ditches are open, the lambs fall into them and can't get out, whereas when they're blocked, they've either got water in them or they've got vegetation in them, and the lambs can walk across. Same for grouse and waders as well. Wader chicks easily fall into some of these ditches, so actually by blocking them, it's got a lot of other benefit from actually doing that. And what we're hoping with restoration is it's actually not just seen as one benefit, it's actually seen as multiple benefits, both to society, to wildlife, and the whole environment.
Hope you enjoyed this program of ours. End of a very hard day. Time to relax, and the scientists have left the building.